So in this set of notes, we're going to think about all the different factors we can imagine influencing the kinetics of an exchange reaction. And we're going to use that to be able to predict which complex is more likely to be more inert or more labile than another complex. So first we're going to look at the effect of multidentate ligands. And we're going to begin by looking at an example with two monodentate ligands, X, being replaced by some incoming ligand Y. So it really doesn't matter whether this is an associative or dissociative reaction, but in this case we're going to think of it as dissociative. And so if our metal complex is getting replaced, first we have to lose one of these ligands, and so it's in red. So we're going to lose our X in the first step of the reaction, which is typically the rate determining step, generating this 5-coordinate complex here with a space. This box here represents a space that's empty. And then the incoming ligand Y comes in and replaces it and ends up on our complex. Okay? So that would be the first step in the reaction. And then in the second step, it happens again, right? So we have the other X, which is then going to get replaced. And of course, every one of these steps is reversible. And so the overall rate of the reaction is the sum of all of these different individual constants, but most importantly, the rate determining step. So here's our next rate determining step, losing that X, making a box, a space, in which is then replaced by your incoming ligand. Okay, so that first reaction is slow. The second reaction, filling in each case, this empty space is faster. And so we have two different rate determining steps. So let's compare this to what happens if our complex contained a multidentate ligand. So here we're going to think about a complex which contains these two X ligands bound together. Maybe this represents ethylene diamine or something like that, right? But these are the same two ligands we're going to replace, and we're going to think about how this changes when these things are bound together as a multidentate ligand. So we're still going to have a first dissociative event where this particular ligand portion dissociates from the metal. So the complex has to twist, this ligand has to twist away from the metal, still bound by the other side, making a space where the incoming group Y can come in, right? And so it's notable that this is very slow now. It's slower than it was in the monodentate case for an important reason, right? That when these are tied together by this bond, that bond has to twist. It actually has to distort in order to make that space open. And so that slows down the reaction. And also, it's important that the reverse reaction, where you regain the ligand that fills in this box with an X, right? That happens very fast. And that's because this other ligand here, right, is very close and can easily bounce right back into that box. And so this is highly reversible. So the fact that it's very slow in the forward direction and very fast in the reverse direction is an important kinetic effect, and that also helps influence that equilibrium effect as well. So in step 2 of this reaction, you then displace the other X ligand here, and this happens really the same as in the monodentate case. The ligand dissociates, makes an open box here, which is then replaced by your incoming ligand. But this very, very slow first step here really drives what's called the kinetic chelate effect. And it's found that this effect reduces the rate of these reactions for multidentate ligands by 20 to 10,000 times. So just to walk back a little bit, there's a thermodynamic effect driven by entropy mainly, and now there's also this kinetic chelate effect, this kinetic effect, which slows the reactions. So multidentate ligands are thermodynamically more stable, and they're also slower to exchange. So next we're going to look at how rate constants vary for different complexes. And these are for different metals in the complexes. And so this is a plot showing the log of rate constants going from very fast reactions on the right to very, very slow reactions on the left. Okay, so the reactions on the right are very fast. We call those labile complex on the left. Labile complexes. And on the left, we have inert complexes, right? So the most inert complex on this whole table is rhodium-3, and the most labile complex is maybe cesium, okay? So these are all, I should point out, they're all aqua complexes, and we're exchanging it with water, okay? So let's think about these different categories. And so on the very top line here, we have +1 ions. These are just simple alkali metals. And we'll see the fastest of those is the largest of those metals, and the slowest reaction of this series is lithium, which is the smallest of those metals. That also is proportional to the acid strength, right? All right, so the next line we have +2 metals, the alkaline earth metals, going from barium all the way to beryllium. So beryllium is beginning to creep towards inert. This is maybe its metalloid behavior, its sort of stronger acid nature also taking into account there. And then there's a big line of transition metals, and these are in kind of a confusing order, right? We've got copper, and then we have way over here vanadium, and then ruthenium, a larger one, right? These are all +2 transition metals. We're going to come back to that. Here's some more +2 transition metals, but these are the group 10. These are the D10 metals. So these have a filled d orbital shell. You see all these are fairly labile. They're fairly fast to exchange. Next line are +3. These are group 3 metals along with yttrium in there. And so those also go roughly in order of size, decreasing size, becoming more acidic, more inert. And then we have the +3 transition metals, okay? And then later down here we have some oxide complexes. So, the real question is, the alkali metals have a reasonable order, the alkaline earth metals have a reasonable order. What is going on with these transition metals, right? Okay, it's going to take some more digging to figure out these factors. So let's first look at the effect of metal oxidation state, and this was in that last table, but now we're looking at a table of data now where we can break this out a little bit more carefully. So I have here broken out really in order of the number of d electrons we have. We're going to just pay attention to that column as we go. And so I have highlighted pairs where we have the same count. There's only 2 pairs in this set of data where we have the same d electron count. And we're thinking of this as different oxidation states, different charges, right? So iron 3 versus manganese 2, those have both 5 d electrons, and they're both high spin in the complexes we're looking at. These are also all, by the way, water exchange reactions, just like what we saw before. So if we look at the rates, the lower charged metal, sodium here, is way faster than the +3. This is 9 orders of magnitude. Amazing, right? The half-life for this reaction, if we want to think about it this way, is how long it takes for half of the waters to exchange. And so for aluminum, it takes about a second for half of the waters on aluminum to exchange with other waters. So you dissolve aluminum ions in water. They actually don't last long that way. But if they're exchanging, they would occur at about 1 second. Half of them would go, or it's a nanosecond for the sodium. That's happening essentially at the rate of collision of water with that sodium ion. A similar trend is here with manganese and iron. So the +3 iron with the same electron count, same electronics, is about 5 orders of magnitude slower than manganese. Okay, so not as dramatic as the sodium and aluminum, but also it's only +1 charge difference, right? Manganese 2 versus iron 3. So in general, the higher the oxidation state, the slower the exchange will occur, all else being equal. Let's look now at John Teller distortion, the effect. This is a very large effect in our metal complexes. And of course, we don't have any distortion in D0 complexes. We're just going to ignore that for now. These are color-coded, so the complexes with no distortion, that's a D3 complex with all of the electrons in the T2G orbital, right? That has no distortion. Or equal occupancy in T2G and EG is also undistorted. So we see those are the cases for D3, D5, D8, and D10, right? And so let's take a look at these rate constants. And there's sometimes other things happening here, so we have to be a little bit careful. But we see, in general, we have a very slow reaction here, 10 to the -6. But we're going to find that these rate constants, even though this one's quite large, right? 10 to the 2 is not very large compared to some of the other constants we'll see, 10 to the 6, for example, right? 10 to the 4 is pretty slow compared to its neighbors, right? 10 to the 7 is even slow compared to the neighbor directly above it. So undistorted complexes tend to be relatively slow to exchange. And let's go to the other extreme, the strongly distorted in yellow, right? So there's only 2 examples of that in this data. So the D4 high spin has this unequal occupancy in the EG orbital, right? And likewise, the copper plus, this is D9, has 3 electrons in the Eg orbital. So one of them is unpaired, one of them is unequal. And those are the 2 fastest rates we have for our transition metals. We have 10 to the 8 rate constant and 10 to the 9. Okay? So strongly distorted complexes exchange very fast. So let's think about why that might be, right? Jean-Teller distortion generally involves either the lengthening or compressing of a bond in the octahedron. Okay, so let's imagine that it's lengthening. So in that case, what we have is a relatively weak bond in one direction. Or you could say that you're opening up space for association if it's associative. In most of these reactions we're going to see are dissociative, but there's a few examples of associative reactions. Both of the strongly distorted complexes are dissociative in their reaction, I think, because of this nature of this weak bond. And so if there is a longer, weaker bond that's driven, in order to lower the overall energy of the complex, then it's easier to break that bond, and that will be the one that dissociates. So Jean-Teller distorted complexes tend to be labile. Let's look at the mechanism now. Okay, that's this column, and these are labeled as associative or dissociative or interchange reactions which favor one or the other, right? Let's see if there's any general trend here and think about why it might be. So 5 of these reactions in this table are listed as either associative or an interchange associative mechanism. And let's just kind of look at this group of rate constants compared to the other group. So if you look at the blue rate constants here, 10 to the 8, 10 to the 6, 10 to the 4, 10 to the 9, right? So you could say it ranges between 10 to the 4 to 10 to the 9. That's the slowest and the fastest of this group. It's not, this is just an example, but this is representative. So on the other side, we have these associative or interchange reactions, and our slowest is 10 to the negative 6, and our fastest is 10 to the 7, right? So 10 to the negative 6 is tremendously slow compared to everything else here. And this is a chromium-3 complex, and there's other reasons why it's so slow. But, here's 500, right? This is, you could say 10 to the 2 or something. Pretty slow also. And this one doesn't have as many things going for it as we'll see the chromium-3 does. And so we could say in general, it looks like the associative reactions tend to be slower, right, or more inert. And why would that be? Well, remember, associative reactions are related to an SN2 kind of like reaction where something has to come in and associate at the same time, right? Your incoming ligand, we've been calling it Y, has to come in and bind that metal. So octahedral complexes, you could say, are generally crowded. They're generally sterically hindered because there's stuff in all of these 6 positions, right? It doesn't matter how small they are. There's still a lot of stuff crowding that metal center. And for an SN2 reaction, you might recall that steric hindrance slows reactions. So if your reaction is required to be associative, meaning that these bonds here are difficult to break, so you have to have something come in and start that reaction going, then it's going to tend to be difficult, okay? And so that is, it's just generally true that for an octahedral complex, associative reactions tend to be slower. It's just difficult to get them going. Whereas if it's dissociative, that's assisted by steric crowding, right? If there's steric crowding, these things are more easily removed from the metal. And so that drives the reaction forward. Let's take a look at one more column here, which is the ligand field stabilization energy, right? These are the values we calculated before. And let's see if there's any pattern between the rate of the reaction and this value, all right? So let's just look at the 2 extremes, the one with the most ligand field stabilization energy here and here. These are all high spin complexes. Everything in this table is a high spin complex, so they never get larger than negative 6/5. And that's just what happens when you have a lot of electrons in the lower T2G orbital and not too many in the EG, or none in this case. And let's compare that to ones with no ligand field stabilization energy. So these are the ones that are equally occupied in T2G and EG. What we tend to see is that complexes that have a high ligand field stabilization energy tend to be very slow or inert, right? Even 10 to the 4 here in this complex is quite slow compared to its neighbors. Whereas if you have a complex with no ligand field stabilization energy, the reaction tends to be pretty fast. So 10 to the 7 is pretty fast. It's not the fastest, right? 10 to the 9 here for copper was faster, but we saw that was because that one was strongly distorted. In fact, these complexes here are undistorted, as is the D10, right? And so those do have no Jahn-Teller distortion helping them, but they do have this sort of thermodynamic factor here in this ligand field stabilization energy, which are speeding their reaction. So why would this be? We talked before about how the T2G and the EG orbitals are representing sort of the difference in energy between these orbitals and what they would be if they were unsplit. You could think of this in this crystal field this old way, or you could just think of them in terms of where they would be if they were in a spherical environment of ligands, of bonds, right? In either case, the T2G orbitals, by splitting lower than that sort of neutral point, do thermodynamically stabilize the complex, even if these are non-bonding orbitals. The EG orbitals, if they're occupied, they sort of destabilize this complex. They're going to make it easier to dissociate or react. So that ligand field stabilization energy is closely tied. We'll see that in the kinetic reaction, really, we always have to think about the starting point and then the ending point. Where are we in our intermediate or our activated complex, our transition state? So we have to compare those two. And so we're actually going to elaborate on this a little bit more later and add a new column, which is even more accurate. But ligand field stabilization energy gives you a good sense, because this is your energy well you're starting in. And if it's very deep, if you're very stabilized by this thing, you're going to have to get yourself out of that. It's going to cost you time. It's going to cost you activation energy. So in general, high, or you could say negative, large negative ligand field stabilization energies make a complex more inert. So to summarize, we saw several different features here. And so let's just think about how to tell whether a complex is inert, right? So a complex is likely to be inert if, first of all, maybe the metal has a high positive oxidation state, right? High charge. And this works even for, the alkali metals versus the alkaline earth metals. The higher the charge density, the slower the reaction, right? So next you can look at Jahn-Teller distortion. Distorted complex react quickly, so undistorted complexes tend to be inert. If you know the reaction mechanism, it's true that most dissociative reactions for octahedral complexes are slower than dissociative reactions. And so if you know that it's associative, it's more likely to be inert. Next, you look for large ligand field stabilization energies. And so this is something that's easy to predict. If you know the d electron count, you can predict, if you know it's low or high spin, of course, you can predict ligand field stabilization energy. And large negative numbers tend to be the most inert complexes. And finally, if you, this is the first thing we talked about here, for multidentate ligands, if you have a polydentate ligand on your complex, it's more likely to be inert. So you can use these factors to try to predict which complex will be more or less inert than another, or more or less labile. So that's what we'll do. So let's work through a few examples of trying to guess which complex is more inert or more labile. We're just going to label I and L for inert or labile, all right? And it's just always relative to another complex. So in our first example here, we have iron 3. So iron 3 is going to be a D5 complex, okay? So they're both D5 in this case. And, we have a cyano complex here, and we have an aqua complex. And so the cyano complex is a very strong field ligand, right? So this is going to be low spin, D6, D5. And our other complex here, the iron aqua complex, is going to be a high spin, D5. Okay, so low spin versus high spin. Well, if we think about our ligand field diagrams here, right? Low spin versus high spin. We can see there's a pretty big difference in, first of all, the ligand field stabilization energy. And that is one of our factors, all right? They're both the same oxidation state. They're both the same metal. They are two different kinds of ligands, but we weren't talking about ligands in this section. We're just talking about the effect of the metal itself. So this high, this high ligand field stabilization energy is going to drive the cyanocomplex to be more inert. And yes, it does have weak Jahn-Teller distortion, but that weak distortion was not a huge factor. If one of these was strongly distorted in one case or the other, then we would start to pay attention to that. But in this case, we're going to say that this cyanocomplex is more inert and the aqua complex is more labile of that pair. Let's look at these two complexes now. So this is cobalt 3 versus iron 2, right? So cobalt 3 versus iron 2, we have a D6 low spin complex here. And the iron amine complex is also going to be a low spin D6. Okay, so same configuration, both low spin. And so let's think about how we can differentiate these, right? They're both amine complexes, but again, we're not paying so much attention to that. Let's pay attention to this, though, right? Iron versus cobalt. If the electron count is the same, the sizes are similar, we're looking at the charge density. So in this case, the higher oxidation state, the more positive oxidation state, is going to favor the inert complex. Okay, so we're going to guess that the cobalt 3 is more inert than the iron 2, all else being equal. All right, so one last example here. Let's look at a copper versus zinc. So they're both the same oxidation state, both positive 2, but copper is D9. There's no high or low spin here, and then zinc is D10. Okay, they're both aqua complexes, but if we think about this diagram here for each of these, we have there's the first 5, 6, 7, 8, 9, right? This is your D9 configuration, and D10, of course, is going to fill in that missing space. But the key to copper at D9 is this, unequal occupancy in that EG orbital. So this is strongly distorted. This is strong Jahn-Teller distortion, and that was one of our largest factors. If we have that strong Jahn-Teller distortion, it is very likely to be labile. Which means, relatively speaking, the zinc will be inert. It is by no means an inert complex, but it's more inert than the copper complex, right? But definitely copper is, no matter how you want to think about it, a labile complex. This is one of the fastest exchange rates we had in our example data. So that's the way you generally think about it. You look at your different factors and you try to find a factor that distinguishes one complex from another.